with some of the general details regarding the course. Okay, so yeah, so that main textbook being used. So actually, one more textbook is there which is not mentioned here. So if you go to the course page, so you will see a list of textbooks in your right hand side. Okay. So one of them is a online textbook. Yeah. So yeah, all the content for the textbook is available online, and it's a very accessible textbook. We'll be more or less be using that. So another textbook is there, which is this textbook, which is the other textbook that is being used. This textbook, it is actually a pricey textbook. It's not available as a PDF, freely available as a PDF on the web. Okay. But there are some lecture notes based on which this textbook is there. Okay. I have again given the link to the lecture notes in the course website. Okay. So you can see there's a lecture notes link corresponding to this textbook in the course website. So that is more or less similar to the textbook itself. Yeah. Yeah. So so this is another very standard textbook, which is William Feller and Sheldon Ross. These are very standard textbooks in probability. If you have those textbooks, yeah, they are good textbook to follow. But if you don't have them, don't worry about it. So if you if you are very keen and interested about probability, and if you want to explore more, these are good textbook to follow. William Feller and Sheldon Ross. Okay. Um, so especially this textbook is a very old textbook, which has like lot of examples of probability used in many fields. Okay. So finally, there is also a MIT OCW course. Yeah. So this is actually a complete course with videos, tutorials, solved problems, exams, assignments, everything. The full content is already there. Yeah. So this is this is extra material. So if you want to explore more, you can go there, try solving some problems. Yeah. Yeah. So you will have enough online material for learning this course. Okay, the textbook is available online, as well as there's a large reference material which is including videos, assignments, and everything, including solved problems available online. So there's also you can see a link to my previous version of this course in my in the course website in the eLearn portal. Okay. So yeah, that's about the textbooks. Yeah. So yeah. So you are you are this is possibly for the undergrad students, but yeah, you need to be regular in this class. Okay. So we'll be quickly moving through the topics. This is a half course, and we have to learn probability in this short half course. This is typically taught as a full course. So the assumption is that okay, many of you already have learned probability before, right? Many of you already have learned probability before, and this is just refreshing your memory, right? So yeah, be regular. The only way to learn probability is by solving problems. There's no other way to learn probability. Yeah, simply reading a book, you will not learn probability. You need to solve tens and hundreds of problems. Yeah, by the end of this course, by the mid of this course, you have to at least solve 100 problems. Then you will learn probability. Yeah, so that's the only way for learning this, really speaking. Uh, and yeah, so again, many of this is not applicable to you. So we will try to schedule as much as question answering sessions online. Okay, so uh, so during my lectures, regular lectures that we have like this, we'll be trying to solve more and more problems, examples and problems. You can ask questions about the problems, and more discussions happens during the scheduled lecture hours. Yeah. So what I suggest is you go through the textbook. I will share the reading material of the things I'm going to cover in the class ahead of time. I'll be sharing the exact page numbers. I will also be sharing a video link to MIT OCW. So you can go through this material, and during the lecture I will be again going through the same material, but the focus will be on solving problems. Okay, solving lot of examples on class and clearing your doubts. Okay, so in a typical class we can have exams and we can talk to each other and solve problems. That will be missing this way, but we can recover a bit of it by spending more of this live time, discussing things and solving problems. Okay, so yeah, so so this is the way which is going to be good for the class. So I'll be sending you a questionnaire about if you have any issues with this mode of teaching. Yeah, because yeah, this also require cooperation from you. Okay, otherwise all I can do is I can just explain the theory in the class. We will have very less of discussions going on. Okay, so yeah, this is going to be the mode of the class, unless if there is a major objection or anything like that. So yeah, so you will need to go through the textbook, maybe possibly look at the videos and come to the lecture. And the lecture I will be again explaining, just setting up the basic definition, and we will be solving problems. Okay, this will be new problems which is not there in the textbook or anywhere else. Yeah, fine. So let's get started. Yeah, so let's get started. So this is the general things we are going to cover in today's lecture. Okay, so when you start with probability, okay, so what is probability? Yeah, probability is used in various different fields in very different ways. So it's very difficult to in one word say what probability is. Okay, so for example, yeah, take the field of computer science. Okay, now you might, for example, how is your passwords being created? So when you sign in, some random value is being which is used as a secret key to log you in. So those passwords are randomly generated. Yeah. So there's an application of randomization there. It's a very different application from, let's say you want to model what is going to be the weather the next day. The weather is going to be, it is going to be something deterministic the next day. But if you, from today, if you want to predict the weather tomorrow, it is uncertain. Yeah. But from the previous year's experience, we know, yeah, tomorrow's weather is how it will be or something. We also, let's say the meteorology department has lot of sensors sitting all around the place, and they have some information from the sensors. But even from that, they cannot be completely certain what the weather is going to be tomorrow. Yeah? So they will have a probabilistic model saying that, okay, it is going to be with this much probability, raining, this much probability it's going to be sunny, this much probability it is going to be cloudy. So yeah, so whenever there is some uncertainty, whenever you don't want to know, you don't know for sure, you use probability. Yeah. So another very common thing nowadays is in machine learning, right? So many a times, okay, let's say you want to classify between cats and dogs, okay? And sometimes you get some figures from the picture you are not able to distinguish between a cat and a dog. It is some odd pose because of which it's not sure it's a cat or a dog, okay? So in which case you might want to answer, give a probabilistic answer. Okay, this is 50% cat, 50% dog, which doesn't mean anything, but yeah, you could have various ranges, right? 70% dog, 30% cat. Yeah, so yeah, it is used in various fields. It's used in, for example, in physics. There is quantum mechanics. Okay, and there's a lot of randomization in quantum mechanics. When you measure a quantum mechanical system, you will only be able to say with probabilities. Okay, so yeah, so yeah, so there is a Schrodinger's cat example, right? The cat is sitting inside a box, and there is some nuclear material also inside. So if you open the box, yeah, there is some probability that the cat is alive, some probability it is not. Right? So actually the quantum mechanics goes beyond probability. It goes into complex vector spaces and all. But still, yeah, you need, it is built on top of probability. So there are plenty of examples, and let's get started with some basics of probability. Okay. So yeah, so before you get started with analyzing any probabilistic system, the first word you should understand is the sample space. Okay. Sample space is basically a set. It is a set of all possible outcomes of the experiment. Right. So before you start talking about probability, first thing you need to do is find the set of all possible outcomes that your experiment can have. Okay, and without defining this, probability doesn't make sense. Yeah, first you need to find out, okay, what are the list of outcomes possible. Yeah, so let's say you are tossing a coin. Yeah? So what is the list? What is the possible outcomes? Yeah. So, I mean, yeah, you can make some reasonable assumptions that the coin will not stand vertically like that. Then it can only be head or tail. Yeah. So the set of all possible outcomes is just head, comma, tail. It's very plain and simple. Okay. Now, suppose let's look at a slightly more complicated example. You throw a dice. Right? It has 6 sides, and you throw a dice. Now you can say the sample space is 1, 2, 2 up to 6. Yeah. But what if you throw a pair of dice? Yeah. What if you throw a pair of dice? Yeah. And how many? The experiment is going to be conducted in multiple ways. So yeah. What is the number of possibilities if you throw a pair of dice? Anybody? What is the sample space?
36. 2 to 12.
36.
Okay. Yeah. So they express it concisely. You can say just 1 to 6 cross 1 to 6. Okay. This is the set theory cross product. Okay. Everybody knows set theory cross product, and this is nothing but the set of I comma j, where I comma j belongs to 1 to 6. Is this clear? It's just a cross product of. Yeah. But now, if you think about it carefully, there is something weird happening. Yeah. It also depends on how you set up the experiment. Can you imagine why this cannot be 36? Anybody has, yeah, anybody can think of a way why this cannot be 36, the number of possibilities?
What if two sides are having the same numbers?
Yeah, sure. But let's assume that all the sides have different numbers.
In case of biasness?
Also, the number of possibilities is the same, no?
Okay, yeah.
Probabilities might vary, but the number of possibilities is still the same.
So in case both the dice show the same number, it would be able to distinguish. It would be able to distinguish. It would be difficult to distinguish which dice is which number.
That is right. So Amisha's voice was not very clear, but let me just rephrase what she was saying. It is that suppose both the dice look identical. Yeah. And somebody throw the dice, and then you are only seeing the picture. You didn't see, okay, which order it was thrown or anything like that. Somebody threw the die, and then you are seeing the picture of what came up. Does it really matter if, I mean, maybe the guy throwing the die knows which was the first die he threw, which was the second die he threw. Yeah. But you are seeing after he threw the die, and then you are opening the door and seeing it. Now you don't know which was the first die and which was the second die, because both the dice are identical. Yeah. So it doesn't matter if I saw the, I mean, the first die was 1 and the second die was 2, or the first die was 2 and the second die was 1, you are saying the identical picture, right? I mean, here if you look at it, the element in the sample space 1, 2 and 2, 1, these are two different elements in the sample space, right? But maybe you cannot distinguish between them because somebody else threw the die, the first die and the second die, and then he invited you in to the room. Yeah. So yeah, we have to be careful about experiments. Yeah. So we have to be careful about experiments. How do you assign probabilities? We need to understand, yeah, what are the different possibilities. Sometimes I mean, what we think intuitively is the sample space might not be the sample space. Yeah. So is that clear? Why this thing should be the same if the experiment is conducted differently? Does anybody have any comments regarding that? Yeah. So what is the sample space in the second, if suppose the experiment is conducted like somebody throw the first die, somebody throw the second die, and then you are being invited into the room. Yeah. How many possibilities are there? And what is the sample space? Yeah. So, yes, how will you describe the sample space in that case?
It's 21.
It is 21. Okay, why do we say 21?
For one, the possible, if first dice is 1, then for 6 possibilities are there for second dice. And if the outcome of first dice is 2, then second dice also 5 possibilities are there. Because 1 is already included in the first experiment. So 6 plus 5 plus 4 plus 3 plus 2.
Okay, so let me just try to count it slightly differently. Okay, so there are 6 cases when, I mean, both the dice are same, right?
Yes, sir.
Yeah. So there are 6 cases when both the dice are same, and when both the dice are different, how many possibilities are there?
6 choose 2.
Choose 2, right?
Okay.
So 6 into 5 divided by 1 into 2, that is 15, plus 6 equal to 21. Yeah. Yeah. Is this clear how I counted here? The first
Yes.
case was when both the dice were the same. Yeah.
Yes,
The
sir.
second case, let's assume that both the dice were different. Then how many possibilities are there? You
Yes.
don't need to order them. 6 choose 2. Yeah.
Yes.
Earlier, you were actually doing ordering of it. It was actually instead of 6 choose 2 into 2 factorial you are doing. So yeah, this is the second experiment, and this is the first experiment, if you want to put it in the right context. Yeah, so this will work out to 36, I guess. Yeah. Yeah. So yeah, so this business is slightly tricky sometimes. Okay, so you need to know how to count. Yeah, if you remember your old combinatorics, discrete maths, all those things you need to recollect. Okay, so if you actually, so there is this probability course website. So yeah, the first chapter of it will, you will get some, if you go through it, you will get some background about, okay, set theory, Venn diagrams, if you just want to refresh it. What do you mean by one, on, two functions? How do you do basic counting? Like, yeah, how do you count? Yeah, all those things you have to do. Okay, so there is some, sometimes you need to order things, sometimes you just need to choose things. Yeah, so here we are just choosing two things, here we are choosing two things and also ordering them. Yeah, so you need to understand the differences between these things. Okay, I assume that you know all these things because you are yeah, senior grad students. Okay, so yeah, fine. So now we know, okay, what are the possibilities? Yeah, somebody want to say something?
Sir, I wanted to ask that how do we model the sample space? Like, if it's just given a pair of dice, then how would, like, we know that whether we have to take the ordered sample space or we have to take an unordered sample space, or whether there can be different, different sample spaces for the same experiment.
Amnisha, you have some background noise. Yeah. So, yeah. So I understood your question. So, okay, how do you choose the probabilities? How do you choose the sample space? Okay. One answer is it depends upon the experiment. Maybe okay, you were modeling a situation where the two dice had different colors. So one was a red die, one was a blue die. In which case you can distinguish. And the first, the 36 size sample space is obviously the right choice, right? Or you saw, I mean, that the one guy threw the dice once, then he took out and then threw the second time. So you know the difference between the first time and the second time, right? So in that case, it is obviously this sample space. But suppose the experiment was conducted behind closed doors and then you are invited in, yeah, then it is the second. So it depends upon the problem definition. So you read the problem carefully, you read your situation carefully, and then you decide which one to choose. Okay, and sometimes, yeah, many times it occurs in physics that you don't even know which are the two cases. So you try both cases and see in experiments, okay, which is the right probability model. Okay, so in fact, this is a fundamental problem in physics. Okay, so there is something called, yeah, we will come to that maybe. Okay, whether it's ordered or unordered is actually a very fundamental problem in physics. Okay, yeah, somebody else had a question.
Thank you, sir.
So let's answer some simple questions here, right? Yeah. So suppose you threw a pair of dice and suppose it is this case. Yeah. So what is the probability of seeing 1, 2? Yeah. So yeah, to answer that, you will ask, okay, is the die proper? Like is it fair? Yeah. What do you mean by fair? All the 6 possibilities are equally likely. Are equally likely. What does that mean? There are 6 possibilities. So the probability of seeing 1 is 1 by 6, 2 is 1 by 6. Any of them is also 1 by 6. Yeah. So how do you compute the probability of seeing 1, 2? Yeah. Yeah. So there are 36 possibilities. Yeah. All of them are equally likely. So it is 1 by 36. Yeah, so this is one particular instance of this set. Yeah. And there are 36 possibilities, so it is 1 by 36. It's equally likely. It's a fair die. Okay. Now let's ask a different question. What is the probability of seeing at least 1, 1? How do you compute that? How do you compute the probability of seeing at least 1, 1?
Excuse me, sir.
Yes.
So before moving on to this question, could you please explain the previous one? I couldn't get it.
Yes. So there are 36 possibilities here, no? There are 1 to 6 into 1 to 6. 36 possibilities here. Yeah. So that's why the denominator is 36. And what is the number of cases included in the probability? Yeah. It is only one pair is the favorable case. The first one has to be 1, second one has to be 2.
Understood, sir. Understood. Understood. Sorry.
So
Thank
all
you.
the 36 have equally likely, and yeah, it has to be 1 by 36. Yeah.
Yes, sir.
I'm not looking at the second case. Yeah, you can ask the same questions in the second case. Yeah, and you will get again you will get into some complications. Okay. How, okay, is the 21 things equally likely? Do you think the 21 things are going to be equally likely if the experiment is conducted? Okay, somebody threw 2 dice, then you were invited into the room, and then you saw the 2 dice. You cannot distinguish between the dice. Are all the 21 possibilities equally likely? What do you think?
No, sir.
No, sir.
Identical will have less probability.
Yes.
Yeah. So the probability of seeing, this is the second case. Okay. So this is the second case. The probability of seeing 1 is going to be how much? Could anybody make a guess?
6.
1 by 21.
It's going to be 1 by 21. Are you saying that all these 21 possibilities are equally likely?
1 by 36.
1 by 36.
1 by 36.
Okay. Why 1 by 36? Yeah. So the interesting thing is the sample space here is actually obtained from the sample space here by joining some elements, right? The sample space in this case is obtained by the sample space of this space by uniting some elements. Whenever you had 1, 2 and 2, 1, you just united them into one element in this sample space, in this smaller sample space. Yeah. So this sample space is also coming from this bigger sample space by joining elements together, right? So 1, 1, you are not joining 2 elements. It is just a single element in this original 36 space, which we are keeping, right? And that is why this is equal to 1 by 36. But when you look at the probability of 1, 2, so I should actually write set 1, 2. Yeah, to be clear, what is this? The order between 1 and 2 doesn't matter. Yeah, the probability of 1, 2 is, it is actually the probability of 1, 2 or 2, 1 in the bigger sample space. This is in the bigger sample space. That is going to be 2 by 36. It's 1 by 13. Yeah, is that making sense? Does that make sense?
2 by 36 is 1 by 18, right?
Yeah, of course. Yeah, I need to work on my basic math. Yeah, anyway, thank you.
Explain one again.
You want to explain this again? Okay. So,
So 1 by 36, when the sample space is 21, how 36 can be there?
yes. Okay. Now, so remember how the experiment happened, right? So somebody threw the first die, and then he threw the second die. So he knows the difference between the first die and the second die. So that person who threw the die, yeah, he is actually seeing all the 36 possibilities. Yeah, and all of them are equally likely. For the person who threw the die, it is like this sample space, the first case. But now you are just being invited in. So this happened behind closed doors, and then you are being invited in. But you don't know the difference between the 2 dice. Yeah, but suppose the guy who threw it, suppose the output was 1, 1. Yeah. Now, from the sample space of the guy who threw it, there is only one element corresponding to what you also see. That is why this is 1 by 36. But suppose when the guy threw it, the output was 1 2, yeah, or the output was 2 1. In both those two cases, you will be seeing 1 and 2, right? Yeah. So the probability of you seeing 1 and 2, yeah, is equal to the probability of the guy who threw it seeing 1 2 or 2 1. You agree?
Sir, then this is relative, that whether the person is throwing or the one who is seeing.
Yes. I mean,
Then we have
yeah.
to answer in
But,
which.
no, but the sample space are different. For the person throwing it, the sample space is this bigger space, and for the person being invited in, the sample space is 21-dimensional space. The probabilities here are equally likely. The probabilities in this 21 space is not equally likely. It is for some elements it's 1 by 36, for other elements it's 1 by 18, right?
So, sir, then we have to answer in which reference, the one who is throwing or the one who is seeing.
So it depends on whose point of view you are asking the question. So first I asked the question from the point of view of the thrower, and then we answered 1 by 36. Yeah. And the next we answered the question, that is, I explicitly mentioned second case, that is you are being invited in. In that case, this is the answer. So it depends upon the reference. And in the first reference, the answer is this. Actually, you could put 1 2 or anything here. It's always 1 by 36. And if you are being invited in, it's going to be the second answer. Yeah, does that make sense?
Okay.
So yeah, when you attempt a problem, you should think from whose point of view are actually looking at the system. Yeah. And it's possible, and both of this way of looking at it will help you. For example, we arrived at these probabilities in the second case by actually looking at the first case. Yeah. We counted how many possibilities in the first case was being merged to get an instance in the second case. Yeah. So the first probability space, the uniform probability space, are easy to analyze. Yeah. And the second case, it's a non-uniform probability space. You need to be a bit more careful. Okay. Fine. Okay. So for now, let's stick with the first case. Yeah. So unless otherwise stated, everything will be uniform. Yeah. But we'll also be looking at non-uniform cases as well. Okay. So yeah, what is the probability of seeing at least 1 1 in the first case?
0.96.
11 by 36.
Yeah, I would prefer the second answer to the first, and even in your exams, you don't need to compute the decimal places or anything. You can just write down the number as numerator and denominator. Okay.
Okay, sir.
So it's good that you are calculating and saying, but the idea is the course is not about the calculation. It's about reasoning out the probabilities. Yeah. Okay. So how do you get this answer? Yeah. So in how many possibilities I see at least 1 1? Yeah. So I will see it when the first dice was 1, right? How many possibilities? What is the probability that the first dice is 1? Yeah, so
1 by 6.
Yeah. So let A be the event that first dice is 1. Yeah. B be the event that the second dice is 1. Yeah. So now what is the probability of at least 1 1? It is the probability of A plus probability of B. Is that right?
We have to remove the common.
Yeah. So something is wrong here, right? So what is wrong? So
The intersection case needs to be removed.
yeah. So what I should ideally write is not this. Okay. What I should write is probability of A union B. Okay. Even if A happens or B happens, I am fine. Yeah. But what is probability of A union B? Is it probability of A plus probability of B? Yeah. So if you remember your Venn diagram, A and B could have an intersection. Yeah. And that intersection you'll be counting multiple times if you just add probability of A and probability of B. Right. So you should actually be doing probability of A plus probability of B minus probability of A union B. Right. So if you remember the Venn diagram, there is A, there is B. Yeah.
Sorry, A intersection B.
Sorry, A intersection B. Thank you. Yeah, good that everybody is listening. Yeah. Okay. So yeah. So is that clear? So yeah, your set theory, Venn diagram, all of them come to use here. Okay. So your basics in discrete maths, set theory, counting, combinatorics, all of them will be used here. Okay. So if you feel that okay, you need to revise it, you can go through the initial chapters of the textbook. Okay. If you need more link, if you can go to OCW, there is a discrete math course also there. You can just go through some problems, revise it a bit. Okay. So any questions about any of this?
Sir, in terms of the course of action, so could you please guide us like properly? What are links to study from, and what are books or chapters to study from initially, at least?
Yeah. For every course, every lecture, I will be putting out the exact page numbers you need to read. Okay. But the point is, the reading alone will not help you. Okay. You should read. You should come to lectures, ask questions.
Okay.
Yeah. And you should solve a lot of problems. That's the only way to learn probability. You can read thousands of pages, but you will not learn probability. The only way is you should try some hard problems, think hard. That's the way to learn probability. Okay, and yeah, it is satisfying. You think hard and solve a problem. Take your time and solve the problem. You will feel satisfied. Okay, I learned something. Yeah. And yeah, and that is more important than anything else, in my opinion. Okay, so so let's go on.
Thank you, sir.
Yeah. So yeah, again, it is about this viewpoint thing. I want to stress it a bit more. Yeah. So suppose you have three balls. Okay, you have balls. Let's say it's like labeled A, B, C. Yeah. And you have three bins. You have three baskets. Okay. Again, labeled. It's a red, blue, and green. Yeah? Okay, you have three balls and three bins. Yeah. So how many possibilities are there? Yeah, so yeah, it's already there on the site. 27 possibilities are there. Okay. Yeah. So now let me ask you a different question. Suppose you have three balls and four bins. Yeah, and the four bins are like having different colors. One is red, blue, green, yellow. Yeah. And the balls is A, B, C. How many possibilities are there? What is the size of the sample space?
Sir, 4 cube, 64.
Sorry?
Sir, 4 cube, that is 64.
4 cube. or 3
Yes,
raised to 4?
sir. 4 to the power.
Yes, each ball has 4 options.
Okay.
Bring above 4.
Then each bin also has 3 options, no? Why can't we think of it like that? Yeah, one of you has background noise, so it's better you get a headphones in this kind of situations. Okay, it will be extremely useful, especially in this semester, that you use a headphones for this lectures, so that we can avoid this background noise. Anyway, so
will it be 3 to the power 4?
3 to the power 4. Why do you say 3 to the power 4?
Because for each ball, we have 4 different bins we can place it into.
Okay. For the first ball, I had how many possibilities for the first ball? 4. What about the second ball?
Okay, sorry.
So for the second ball also you had 4 different possibilities. What about the third ball?
3 possibilities.
4 raised to 3. So it is, these are very subtle and you need to think very carefully. That's the moral of the story. Yeah. So yeah, just seeing 2 numbers and yeah, you should think a bit before answering. Okay, these things can be very tricky. Yeah. So yeah, 3 raised to 4, 4 raised to 3 might be like looking very similar, but they are very, very different numbers. Okay. So we need to be extremely careful. Yeah. Okay. So that was just a point. Yeah, we need to be a bit careful about counting. Yeah. So in this case, you don't have any confusion. There is 3 balls and 3 bins. Okay. So you don't need to worry too much about it's both ways will give 3 raised to 3 only. Yeah. Hello everyone, can you hear me?
Yes, sir.
Hello. Yeah.
Yes, sir.
So yeah, I'm having some issue regarding the power. So let me just share my desktop. Yeah. So yeah, there is some power issue. Okay, so we will just follow the desktop. Okay. Okay. So yeah, so we understood why. Yeah. So there are 3 balls, 3 bins. There is no confusion. Okay. So what is the probability that you have one cell, one bin has multiple balls? How do you compute that probability? Yeah, you want to compute the probability of one bin having multiple balls.
So one bin should have at least one ball, right? That is the question.
Once there should be one basket, right?
Sorry, sir, we missed you.
No, the question is there is one, so there are 3 baskets and 3 balls, right? And we are throwing the balls randomly to each of the baskets, right? Is that clear?
Sir, your
No,
voice
sir,
is
we can't
breaking.
hear you. Your voice is
Your voice
breaking.
is breaking.
Okay, just a second. Give me a minute.
So could we approach
Yeah.
this problem thinking that, let's say if we have 4 bins, X, Y, Z, W.
Just give me a minute. Let me just change to a different network so that I can be audible properly.
All right.
Yeah. Hello. Can you hear me?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So yeah. So there are 3 baskets and there are 3 balls, right? And you are being asked the probability that just a second that there is one of the basket which has multiple balls, right? So yeah, what do you think the answer is? How do you find this probability?
So
one,
multiple means more than one, or at least
yeah,
two.
at least 2, yes. Yeah.
Or we can
So
also
there are. Mhm.
we can subtract the case in which 1 minus, we can do like this 1 minus when every cell has single ball. That would be more easy.
Yeah. So when always you have probabilities, okay, you can play a bit of tricks, okay, and this is the first trick in the book, okay, which is whenever somebody asks you for probability of something, don't immediately try to compute that probability. Think whether it is easy to compute the probability of that thing or its complement. Yeah. So one way to think about it is, okay, there are 27 boards. I will go and count how many of these figures have, at least 2 balls in a bin. Maybe it's easier to count the situations when every ball has only, every basket has only 1 ball. How many possibilities are there when every basket has only 1 ball? It is 3 factorial.
3 factorial.
3 factorial. So you just need to do that.
Excuse me, sir.
And then, yes.
So could you please repeat yourself? I just got logged out of Teams, so I had to re-log in. I'm sorry.
Sure. Yeah, sure. So, so the question is, okay, you have these baskets, and what is the probability that there is one basket with at least 2 boards? Okay. And one way to compute this is, okay, there are 27 possibilities, so the denominator is 27. Numerator, you will go and count through the 27 things, how many baskets, how many cases there were one basket with 2 balls, okay, at least 2 balls, and you can do this, okay. But you need to be clever. There are smarter ways of doing things, which is the smarter way is to observe that the complement of this probability is easier to compute. Yeah. So what is the complement of this probability? The complement of this probability is when none of the baskets have more than 1 ball. Yeah. And there are 3 balls and 3 baskets. So every basket has to have at least exactly 1 ball. And there are only 3 factorial possibilities for that. Yeah. So this probability is nothing but 1 minus 6 by 36. Sorry, 27. Second. Yeah. This way it's much easier. Okay. And yeah, always remember this trick. If somebody asks you a probability question, always think, okay, whether I should compute this probability or its complement, and then do 1 minus. Okay. So yeah. Okay, so yeah, we need to be careful the way we approach problems. First thing, understand the sample space. Do we understand the sample space clearly? Yeah. Then do we understand the probabilities of each element in the sample space clearly? Is it with ordering, without ordering? All those things you need to keep in mind. Yeah. And then you should ask, okay, somebody asks you the probability of an event. Don't immediately jump into calculating that. Think whether that or its complement is better to calculate. Yeah. So also we had one more trick in the previous slide. We also saw that we can, kind of decompose the probability of one big event into smaller events. So in the last slide, yeah, we had this case of probability of at least one. We decomposed into two particular events, computed the probability of that, and then obtained the probability of this big event. Yeah? So these are all, good tricks that you can play in probability. Yeah. So, okay. So any questions?
Hello.
Hello, sir.
Yeah. Yeah.
Hello, sir. Can you
Yes.
hear?
Yeah. Please go
Sir,
ahead.
if we have three balls and three bins, then there might be a case when one of the basket can be empty. Like here, we have one cell can have multiple balls. So,
Yeah.
that case should be included, now that one of the basket is empty. Because 6/27 it says that each basket has exactly one ball, but there must be a case that one of the basket might be empty.
If one of the basket is empty, then there will be another basket with at least two balls, no?
Yeah. Okay. Yeah. Okay, sir. I got it.
Yeah. Okay.
Thank
So,
you.
yeah. Okay. So let's look at the second event. What is the probability that the first bin is not empty? Yeah. Yeah. So
1 minus the first bin is empty. So
one
it
minus.
will be 1 minus 8/27, because then it would be like putting 3 balls in 2 bins.
Yeah.
So
So
it
the
will
first
be,
ball can go to the other two bins only. Second ball can go to the other two bins only. Third ball can go to the other two bins only.
yeah,
Divided by 27.
27.
Yeah. So again, the same trick. Okay, there's actually only 5-6 different tricks in probability. Okay. The question is, when you see the problem, you remember all these tricks and then know which one to use. Okay. So if you understand those 6 tricks properly and to recognize it when you see a problem, then you have learned probability. It's actually very simple. Okay. But the thing is, people forget the tricks. That's the problem, and they don't recognize the tricks needed to solve the problem when you see the problem. Okay. So yeah. Okay. So yeah, what is the probability that A and B occur? Both A and B occur. Okay. So what is the question asking? Yeah. So both A and B occur is the probability of A intersection B. Yeah. So A is the set of cases when, yeah, one cell has multiple balls. B is the set of cases when the first bin is empty. And what is the probability that the first bin is not empty, as well as there is some cell with multiple balls? Yeah. How do you compute it? Yeah.
A plus B minus common. Right.
Okay, you are saying probability of A plus probability of B minus
A union B.
probability of A union B. Okay. Yeah. And you know all these answers. So you, of course, you know this and this. Yeah. What about this? What is the probability of A union B?
Sir, the probability would be 0, I guess, because if first bin is not empty, that means it has at least one or more. And in that case, the first case won't be able to, like, we won't be able to satisfy that one.
If the first base is non empty, that means the first bin can contain 1 ball, 2 ball, or 3 ball, right?
Yes.
Yeah. Suppose it is 1 ball. Yeah. Then the first bin doesn't have has only 1 ball, so the second is not yet satisfied. But the
Right.
second bin could have 2 balls, no?
Oh, right. Okay, sorry. The first one is that at least one cell has multiple balls. Sorry. Yeah.
So, I mean,
Hello?
yes.
Sir, we can make cases like when the first bin has 1 ball, second case when the first bin has 2 balls, and the
Yes.
third case when the first bin has all the 3 balls.
Yes.
And then we can distribute the rest of the balls in the rest too.
Nice. Just one important point that just was mentioned. What we did is we decomposed this event, into 3 cases where the first bin has 1 ball, 2 ball, or 3 balls. The interesting things about these 3 cases is all of them are disjoint. Yeah, so we don't need to compute the intersection. Let me just explain. Yeah. So yeah, somehow this is very weird, but let me just try to find some other space. Okay, so let C1 be the event that first bin has 1 ball. Okay, C2 is first bin has 2 ball, exactly 2 ball. Okay, not 1, not exactly 2 ball. And C3 is right. So we have 3 cases. Yeah, the important thing about these 3 cases is we don't need to worry about the intersections. They are disjoint cases. Yeah, they are disjoint. We don't need to worry about the intersections or the unions or anything. So this probability is probability of B1 plus probability of C2 plus probability of C3. Yeah, we don't need to worry about the intersection or union or anything like that. All the 3 sets are disjoint. Yeah. So this is another trick that you have. If you want to compute a complicated probability, you decompose it into disjoint cases and compute the probability independently and add them up. Can you compute the probability of C1? First bin has 1 ball, and of course there is a second case also, and this condition also should the first condition also should be happening.
So the first condition has two options. Like the answer is 2 because our one, like we are left with 2 balls and 2 bins. Although like if we put 1 ball in 1 bin, the other ball also has to come in this bin. So all in all, there are only 2 options.
Yes. So
for the
size of
second,
C1 is there are 2 possibilities for C1. That's what you are saying.
correct, sir. For C2 also, I think there are 2 possibilities, and for C3 we have
Why C2 possibilities?
sir, because if
there is only 1 ball left.
So 1 ball is only left and it could go in either bins, so hence 2.
But the balls are also labeled, no?
The balls are yes, the balls are distinguishable. So 12 for
So
the
12,
C1.
6 and 1.
Yes.
Yeah.
Okay. So there is also what is the size of C1? So the ball that went into the first bin could be any of the 3. We need to fix that first. Yeah. So this answer is
6.
Yeah. So I have to give one ball to the first bin. So it is among the three possibilities. Yeah. And then there are the two other balls has to go somewhere. Yeah. And it has to, both of them has to go into one particular bin. There are two possibilities for the bin. So 3 into 2. Is that correct?
Yes, sir.
Everybody is sure? 100%?
So can that be more?
Sir, 2 square. So it will be 2 square.
Yes.
Why is that 2 square?
Yes, sir.
So because
And
every ball has two possibilities, either second bin or third bin.
But we need the condition that one cell has multiple balls, no? If the second ball went somewhere, the third ball also has to go into the same place.
So we have also to choose in 2 balls.
So, okay, you need to be careful when you count. Okay, so we are throwing 3 balls. Okay, first we need to ensure that the first bin has 1 ball. That we need to make sure. So any of the 3 balls could go into the first bin. So all those possibilities I counted as 3. 3 choose 1. From the 3 balls I chose a ball which went into the first bin. Yeah. Now the 2 of the other balls, whichever the 2 is, they have to go into the same bin, whether the second or the third. The only choice you need to make is the other 2 balls. Let me just complete.
Okay.
Yeah. So the only choice you need to make after you made the choice which ball go into the first bin is which bin should the other 2 balls go into, and that is this 2. Yeah. The first choice you made is which ball should go into the first bin. Yeah. And the second choice you made is which is the other bin into which both the other balls should go. Does that make sense?
Excuse me, sir.
Yes.
So why we are taking both the balls in one bin? Why can't we take one of the ball in the first bin? So multiple balls will be there in the first bin also.
But your condition is C1, the event is first bin has only 1 ball, no? You are counting size of C1.
Okay, okay, fine, yeah. Sorry. Yes, got it.
Yeah. So now we are counting size of C2. So what is size of C2? The first bin has 2 balls. So from the 3 balls, I can choose 2 balls and put it in the first bin. Yeah. And then there is only 1 ball left. That could go into any of the other 2 bins. Yeah. So again, there are only 2 possibilities. So that also works out to be 6. Is that correct?
Yes, sir.
yes, sir.
Nobody has a contradiction to say. I might be wrong. I frequently am wrong in lectures actually. Okay, so nobody seems to raise a question there. So maybe I am correct. Okay, so what about C3? Yeah, the first bin has 3 balls. How many possibilities are there?
One.
All the
One
balls
only.
into
Just one.
only way. I mean, you can look at this picture. I mean, this is the only possibility. Yeah. So you just add the 3 up and divide by 27. You will get the answer. Okay. Yeah. So actually, we are only just I mean, first lecture 45 minutes we had. Yeah. We already learned many of the tricks in probability.
Sir.
Yes.
Sir, in case A, one cell has multiple balls. If we select any one cell 3C1 and populate it with either 2 balls or 3 balls, so is this thing right?
So the one cell has multiple balls. I should rather say some cell has multiple balls to be clear. Okay. Yeah. So it is the probability of that is 1 minus no cell has multiple balls.
Okay. So it is not only for one
Yes,
cell,
sir.
it can be two cell also.
Yeah, it's 1 minus the probability that no cell has multiple balls, but we have 3 balls and 3 bins. The only way this is possible is every bin has exactly 1 ball.
Okay, sir.
Yeah. So we just need to arrange the 3 balls, 3 factorial, which is 6 by 27. Yeah.
Okay, sir.
Okay. So actually we have learned quite a lot in this 45 minutes. Okay. We saw, okay, what is probability, how to compute it, like the number of favorable cases by total number of cases, if it is uniform probability. Yeah, there might be some tricky situations when things are not uniform, as we see. I mean, it depends upon the reference whom you are talking about, and you need to be careful about that. Then we saw how to compute complicated probabilities. You can break down into smaller disjoint events and you can add them up. Even if they are not disjoint, you can use the set theory formula. You can do complements. Yeah, and you need to be careful in counting. 3 balls, 4 bins, 4 balls, 3 bins. Yeah, you need to be careful what you are doing. Okay. Okay, so great. So yeah, we have around maybe we have around 10 minutes more. Yeah, we had just quickly wrap up today.
Sir,
Yes.
sir, I have a doubt. In that question, that when we have 3 balls and 4 bin, sir, how to take that? Whether we have to take the four to the power 3 or 3 to the power 4? How to decide that?
Okay. So you first you are throwing the first ball, right?
Yes, sir.
How many possibilities are there?
4 bins, so 4 possibility.
Yeah. So 4 possibilities for the first ball.
Yes, sir.
Then you are throwing the second ball. How many possibilities?
4 possibility.
Yeah. Should
Yeah.
we multiply these two numbers or add these numbers?
Multiply.
Now, is it clear?
Sir, but when we can see from the reference of bin that first, if we choose the first bin, that bin has 3 possibility of taking the ball. So then then it will come 3 to the power 4.
Okay. So, I mean, there are, okay, 3 balls and 4 bins, right?
Yes, sir.
Yeah. Now, okay, I take the first bin. Okay. And you are saying the first bin has 3 possibilities for the balls.
Yeah.
Is that what is happening?
First bin can take 3 possibility. Okay.
We are throwing the balls into the bins, not the bins into.
Okay, got it, sir.
Yeah, the physics, I mean, the situation also matters. You should think about the situation also. These are not just numbers. There is also a physical situation. Yeah, and this was the same issue in the first case also. Depends upon who the observer is, what his physical situation is. The probabilities will change. It's not just about numbers. Yeah, so you should understand the reference, who is asking the question. Yeah. Now, I mean, you can ask the same question where, let's say, all the bins are of the same color. You cannot distinguish between the bins. You can ask these 3 questions and try to answer. Yeah. That is.
Please repeat.
And you can ask the same question when, let's say, all the 3 bins, all the 3 baskets were of the same color. You cannot distinguish between these baskets.
Okay.
And try to ask the 3 questions here and find out the 3 probabilities. Yeah. Yeah. So you could also ask the question where, okay, the 3 bins, the 3 baskets are of different colors, but the balls were indistinguishable. They were all white cricket balls. What happens? Yeah.
So then you will use stars and bars.
Yeah. So there's also a fourth case where the balls are not distinguishable. All of them are white cricket balls, and the balls are also, all of them, the bins are also, the baskets are also of the same color. Then what you do? Yeah. So
Then will be the partition.
yeah. So think about all these cases. The thing is, when you see a problem, you need to understand which among these different cases your question is. Okay. So the main difficulty people have with probability is they don't understand the problem many a times among these 4 cases. And after you understand the problem, you understand what the sample space is, you understand what the smaller probabilities are, then you need to see, okay, how to decompose your problem into smaller subproblems which are easy to solve, and how to combine that to get the solution. Okay, so okay, yeah, please go ahead.
If the 4 bins are not distinguishable, can we identify which is the first bin?
No, we cannot. So it's like that experiment that we saw in the dice, right? Somebody threw the balls in some 3 balls, and it was behind closed doors, and then you are opening and seeing it. Yeah. So I mean, here it's since yeah, this is something I have been yeah, I'm giving you explicit about balls and bins and opening doors and everything. But in a real life problem, many a times it will not be clear what are these 4 cases. So first thing I want you to realize are there are these 4 different cases. Everything is distinguishable. Only the balls are distinguishable. Only the bins are distinguishable. Both are indistinguishable. There are these 4 cases, and whenever you see a real life problem, you need to see what are the balls, what are the bins, are they distinguishable, are they indistinguishable, and then start working at the problem. Okay, and yeah, I want you to keep this example really in mind. This will come in all sorts of places, all across this course.
I have a doubt.
Yes, yes, please.
Sir, I have a solution that means we can use the De Morgan's law, like we can use like those
Yes,
shall
sure.
have
So I will put
multiple
out a
balls.
quiz. I will put out a quiz about this, and I want all of you to solve the problem. Okay. So it's perfectly fine discussing among you and solving the problem. Perfectly fine. But when you finally answer, you should have the reasoning worked out yourself. When you have, if you have an assignment to submit, you have to write down your own solution. You can discuss with other people. It's fine. You can find out the solution for the other people and everything. But you have to understand it yourself and yourself write the solution. Yeah, that's really important. Okay. So that's all. So one more thing I wanted to quickly mention is the valuation scheme. Okay. So how do you grade this course and everything like that? So if you go to that course website, eLearn website, it is there. So if you look at the evaluations thing, so the plan is we will have around 12 light quizzes. It will be very light quizzes, simple questions. Yeah, and the light quizzes out of the 12, we will be taking best of 9. Yeah, and that will constitute some 30% of the marks. Yeah. So yeah, it will be okay. We do some lecture today evening. You will get a light quiz. Yeah, and one of the questions in the light quiz might be this. Yeah, okay. And you will be getting 12 of these light quizzes, one roughly after every lecture. And you will, if you get the best of 9 correct, I mean best of 9, you'll be getting calculate only looking at the marks for the best 9 quizzes that you have done. Yeah, and that is 30% of the mark. Another 30% comes up with the deep quizzes. So every 2 or 3 lectures, we will be having a slightly more deeper quiz. Okay. So in this 2-3 lectures, you will have enough opportunities to ask doubts, clear your doubts. And after these 3 lectures, I expect you to be okay, understanding things little more deeply. Okay. And you will have a deeper quiz, slightly more involved problems. Okay. So that is the deep quiz. That is another 30% marks. Then there will be assignments for some 30%. Every week I will be giving out some assignments. You will have to write your solution and submit. Okay. Again, there will be some 5 assignments. The best of 4 will be used for, marks will be used for grading. There's also a discussion forum in the course site. You can ask questions there. Yeah. You can also answer questions of others, and highly recommend that you do. Yeah. So if nobody answers a question or the answer to a question is wrong, I will answer them in the lecture. Yeah, and there's actually 5 marks which is reserved for the amount of interaction that you are doing in the discussion forum. I want you to discuss among yourself in the discussion forum, ask questions, answer questions. Yeah. So 5 marks is actually reserved for your discussion in the discussion forum. And finally, there is some 5 marks extra bonus marks which will be reserved. So suppose you do all the assignments well or all the quizzes, okay, of all the 12 quizzes you do, then you will get some extra bonus marks as well. Okay, so that will work out to be 100% marks. Sure, I can share this PDF. Yeah, I will be sharing this PDF. It will be available in that course website. So by today evening itself, if you are not able to log in, please email me and make sure that you get your login working. Okay. So yeah, that's all for today. We are out of time. Thank you. Sorry, we are really out of time. You will, yeah. So sorry, when did this lecture start? Oh, actually, we are over time. Sorry, I mean, sorry. Yeah, sorry. Yeah, I thought it was 11 o'clock. Sorry. Bye.
It was till 10:30.
It was still 10:30. Yeah. So I made a mistake. Sorry. Yeah.